Hello, welcome to Lab 3. The purpose of this lab is to calculate the mass of a black hole given the position over time data of a star under the influence of the black hole's gravitational field. In this lab we will construct a computer model to analyze the given data, use the model to calculate the mass, which will explain my result that the mass of the black hole is equal to 2.387 times 10 to the 31st kilograms, and answer the what if and what does it mean questions. Our system consists of the star and the black hole. This is the mass of the star, and its position over time is located in the stardata.csv file. The mass of the black hole is the unknown we are trying to find in this lab. This is the black hole's initial position, and we will assume that the black hole remains stationary throughout this simulation. I will now cover the physics applied to my model. First, to analyze the data from the star, I use the derivative form of the momentum principle. The derivative of momentum with respect to time is equivalent to the net force. This can be broken into parallel and perpendicular components. By decomposing the momentum into its magnitude and direction, and applying the product rule, we find that dp dt parallel is equal to d magnitude of p dt times p hat, and dp dt perpendicular is equivalent to the magnitude of p times dp hat dt. To calculate the mass of the black hole, I use Newton's universal law of gravity, with mass 1 being the mass of the star, mass 2 being the mass of the black hole, and the vector r being the displacement from the star to the black hole, and with the appropriate value for the gravitational constant, big G. By solving this formula for the mass of the black hole, we now have a way to calculate the mass of the black hole in our computer model. For the purposes of this analysis, we will assume that all forces acting upon the star, except for the force of gravity, are negligible. We will also assume that dp dt is equal to delta p over delta t. I will now discuss my computer model. Here you can see I have set the position of the black hole to the position which I showed earlier. I have input the star's mass and set big G to the appropriate value, and delta t is set to 1 day. These lines calculate the distance between the x components of two consecutive positions. Dividing this by delta t, we have an approximate for the x component of velocity. These lines do the same for the y component. We use these calculations to determine the initial and final velocity through each time step in the data, which we then use to calculate the initial and final momentum. Using this, we can calculate delta v and delta p, and, based on our earlier assumption, we set dp dt to be equal to delta p over delta t, and we set the net force equal to that value. We then calculate d magnitude of p dt, which, by using the formula we derived earlier, we can use to calculate dp dt parallel, which we then set as the value of f net parallel. We can then simply subtract dp dt parallel from dp dt to calculate dp dt perpendicular, which we will use for f net perpendicular. Now, to calculate the mass of the black hole, I set r to be the displacement from the star to the black hole, and wrote out Newton's universal law of gravitation solved for the mass of the black hole. Here, you can see a model of the star's motion, with the yellow sphere being the star, and the yellow, blue, and white arrows being f net perpendicular, and f net parallel respectively, and the white sphere being the black hole. Here you can see that our computational model calculated the black hole's mass to be 2.387 times 10 to the 31st kilograms when rounded to 4 significant digits. We will now answer the two questions. First, what does it mean? What is the difference between dp dt and its components, and f net and its components? F net is the sum of all forces acting upon a system, while dp dt is the instantaneous result of that force. Therefore, even though dp dt and f net have the same units, magnitude, and direction, they are not the same. For one, dp dt is the resulting effect of the other, f net. Next, what if? If If we replace the original black hole with a new one at the same position, and the motion of the star remained unchanged and is affected only by the force of gravity, is the mass of this new black hole different than that of the first? We will once again use the derivative form of the momentum principle, and in this situation, once again, F net is equal to the gravitational force. Therefore, since the positions, velocity, and momentum are all the same, we conclude that the force of gravity must be the same. If we once again use Newton's universal law of gravitation, solve for the mass of the black hole, we see that all the terms on the right side of the equation are the same for this new black hole as they were for the original. Therefore, we can conclude that this new black hole must have the same mass as the original black hole. This concludes Lab 3.